one of today's most prominent and advanced physicists, has expressed his opinion on the matter. Michio Kaku, recognized for his outstanding contribution to the fields of physics, has recently confirmed that the James Webb Space Telescope has discovered 6 massive galaxies that scientists thought could not exist. These investigations have the potential to open up new dimensions in our scientific understanding of the universe. It is therefore exciting and worth keeping an eye on these developments. Kaku is an outstanding figure in the scientific field, a physicist of American and Japanese origin. He is considered an expert in both classical experimental physics and quantum mechanics. Unlike some more conservative and skeptical scientists, Kaku does not belong to that group and has been receptive to the amazing result of the James Webb Space Telescope mission. We are delighted that this distinguished scientist has decided to break his silence and publicly share what can no longer be denied. The enthusiasm and almost amused tone of the renowned stellar physicist is evident in his comments on the discovery made by the James Webb Space Telescope, expressing that this has been the highlight that has piqued his interest. Join us to discover the implications of Kaku's discovery of these 6 massive galaxies. Michio Kaku is a scientist who has always been willing to consider new theories throughout his life. He is aware that Einstein's equations of relativity in Newton's law are insufficient to capture the full conflicts of the universe. Kaku understands that the discoveries of the new telescope have the potential to enrich the scientific field. Although many of his colleagues have not been able to adopt this view, it is generating concern and insomnia about the Big Bang proponents and opponents of quantum mechanics. However, this only provokes laughter from Michio Kaku. The JW Space Telescope has revealed the discovery of 6 massive galaxies dating back to the earliest times of the universe. Each of these galaxies contains more stars than our own Milky Way. Despite having formed only 200 to 700 million years after the Big Bang, the team astronomers who have made the discovery have duped these exceptional galaxies universe breakers because confirmed they would revolutionize our entire understanding of the universe. Something doesn't fit here anymore. The Big F theory tells us that the cosmos was a hot mess after the initial event. The first solid objects took hundreds of thousands of years to form, and it took hundreds of millions of additional years for the objects to reach sufficient density and produce light. The formation of complex structures such as galaxies was assumed to occur much later. Some of the newly discovered galaxies exceed the Milky Way in size, and their immense luminosity indicates that they were probably forming hundreds of new stars each year, whereas our galaxy forms stars only sporadically. It remains uncertain exactly when the first galaxies formed. Researchers have not been able to determine this so far. The only thing that is clear is that initially there may only have been single stars or group of stars which eventually joined together to form larger and larger accretions until dwarf galaxies developed. The small galaxies encountered other galaxies and gradually grew according to previous theories. Highly organized and massive galaxies could not only have existed at that time, which raises the question of whether the universe is much older than previously believed or whether complex galactic arrangement developed much earlier. This circumstance is difficult to EX for conservative science, which still finds problem with this model, and some branches of physics heavily refuse to accept this discovery and question possible errors in the age calculations. Michio Kaku was aware of this and had this to say: "There are many examples of old and false theories that stubbornly persist because of the prestige of some scientists. Many of these theories were only discredited when a crucial experiment revealed their falsity. Therefore, the fundamental work in any science, especially in physics, rests within the experimentalists who keep the theorists honest. In fact, on Earth, we know very little about the true beginnings of the cosmos. The Big Bang theory was established in 1927 based on observations of the expansion of the universe. These data led to the conclusion that the cosmos originated from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to conceive of a universe with a beginning and an end. The idea of a universe that had always existed and was infinite in time and space was beyond people's imagination, and even today scientists still face difficulties in understanding it. However, it is important to consider these probabilities once again. These new demonstrations do not fit at all with what researchers have based for decades on the Big Bang theory. However, science has shown time and time again that revaluation and openness to new ideas are an integral part of the scientific process, as it is the confirmation of certain theories and observation. When Iceland was a child, it was believed that the stars and planets were firmly fixed in the universe, and these particular structures occupied a defined space. However, we now know that everything in the cosmos is in motion. Planets orbit stars, stars move within their galaxies at hundreds of kilometers per second, and entire galaxies move rapidly through the cosmos, the fate of which we cannot yet even predict today. Scientists are challenged to accept uncomfortable truths and to understand theories are not only guesses and not absolute truths until they are rigorously tested or confirmed by accurate observations. The idea of the Big Bang arose from the realization that galaxies are moving away from each other, and this distance is proportional to the distance to Earth. This observation, known as Hbel's law, suggested that the universe was expanding for a long time. Elements such as cosmic background radiation and the red shy of light from distant galaxies and other cosmological structures seem to support this theory. However, it is important to remember that in the past people who believed that the Earth was flat and that the Sun revolved around us also has this evidence for their assumptions until coincidence or technological improvements came along that provided a clearer and more accurate picture. Right now, we are witnessing a similar situation. Scientists expected the new James Webb Space Telescope to confirm the assumptions related to the Big Bang, but instead they have come across these 6 galaxies that seemed impossible. This reminds us that science is constantly evolving, and that scientists must be open to new discoveries and rethink existing theories based on the available evidence. Researchers use redshift as a tool to determine certain quantities in the study of the cosmos. Redshift, also known as the Doppler effect, refers to the change in the color of the lights as the light sources of the observer move relatively to each other. To understand this, you can imagine standing still and seeing a car coming towards you. As a car moves towards you, you hear the sound of the engine getting louder. However, once the car passes you or moves away from you, the sound of the engine changes. This is because the sound of the engine varies as the car moves. The same is true of light. When a light source such as the lens star moves around us, the light we perceive shifts towards bluer hues. On the other hand, when the light source moves away from us, the light shifts towards redder hues. This phenomenon is called redshift. Physicists have converted redshift's values into velocities and distances for measurement in the study of the cosmos. However, it is important to note that small errors in these measurements could have significant effects. The measurement techniques previously used are currently under review, and it is interesting to see what results scientists will arrive at. As for the latest demonstrations related to our cosmos, it is necessary to consider whether they are really based on redshift errors or whether some scientists are simply denying the facts. This is a question that requires rigorous analysis and careful review of the data and methodologies used in the research. As scientific inquiry progresses, the revelations brought about by instruments like the James Webb Space Telescope, JWST, often challenge our preconceived notions about the universe. The recent discovery of 6 massive galaxies dating back to the early epochs of the cosmos is one such example. These galaxies, which defy conventional theories of galaxy formation, raise profound questions about the timeline and mechanisms involved in the evolution of cosmic structures. The James Webb Space Telescope, successor to the Hubble Space Telescope, is equipped with advanced technologies that enable it to peer deeper into space and observe with unprecedented clarity. Its ability to detect light from the distant reaches of the universe provides astronomers with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and colossal galaxies challenges existing models, which predict that such large structures should have formed much later in the universe's history. The implications of these findings extend beyond astronomy and into the realm of fundamental physics. They force scientists to reconsider established theories about the early universe, including the Big Bang theory, which posits that the universe began from a singular point and has been expanding ever since. While observational evidence such as the cosmic microwave background radiation and the redshift of distant galaxies initially supported this theory, the discovery of galaxies that appear too mature for their age complicates this narrative. Michio Kaku, a prominent physicist known for his work in theoretical physics and popular science, has weighed in on these developments. Kaku, who is known for his ability to bridge complex scientific concepts with accessible explanations, recognizes the transformative potential of the JWST's discoveries. Unlike some of his more skeptical peers, Kaku embraces the notion that new observations should prompt revisions in scientific thinking. He has emphasized the importance of experimental evidence in shaping our understanding of the universe, underscoring that theories must continually evolve to accommodate new data. The debate sparked by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, There are proponents who argue that the discovery of early massive galaxies suggests a longer timeline for galactic evolution than previously thought. This viewpoint challenges the traditional understanding that galaxies grew gradually over billions of years through mergers and accretion of smaller objects. On the other hand, skeptics caution against prematurely discarding established models based on limited observational data. They advocate for a cautious approach, suggesting that anomalies in data interpretation or measurement errors could potentially explain the unexpected findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a crucial role in these astronomical investigations. As galaxies move away from Earth, the light they emit shifts towards longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift in a galaxy spectrum, astronomers can infer its distance from Earth and its velocity relative to our own galaxy. This data is essential for constructing models of cosmic expansion and understanding the distribution of galaxies in the universe. The James Webb Space Telescope's ability to detect faint infrared signals allows it to observe galaxies that are otherwise obscured by dust and gas in the early universe. This capability is crucial for studying the formation of stars and galaxies during the universe's infancy, a period known as cosmic dawn. By analyzing the light emitted by these distant galaxies, astronomers can trace the chemical composition of the early universe and gain insights into the processes that drove the formation of the first stars and galaxies. In addition to its astronomical implications, the discovery of these early massive galaxies raises philosophical questions about the nature of scientific progress and human understanding. Throughout history, scientific paradigms have shifted in response to new discoveries and observations. What once seemed impossible or contradictory to established theories eventually becomes accepted as new evidence emerges. This iterative process of hypothesis, observation, and revision is fundamental to the advancement of knowledge in all scientific disciplines. The concept of a paradigm shift, popularized by philosopher Thomas Kuhn, describes the transformative change that occurs when anomalies in existing theories prompt a fundamental reevaluation of scientific principles. The discovery of early massive galaxies challenges astronomers to reassess their understanding of cosmic evolution and the conditions that gave rise to the galaxies we observe today. It highlights the importance of remaining open to new ideas and revising theories in light of empirical evidence. Cosmologists and astrophysicists are also grappling with the implications of these findings for our understanding of dark matter and dark energy. These elusive components, which together constitute the majority of the universe's mass-energy content, play a critical role in shaping the large-scale structure of the cosmos. The distribution of galaxies and the rate of cosmic expansion are influenced by the gravitational effects of dark matter, while dark energy is thought to drive the accelerated expansion of the universe. The discovery of early massive galaxies provides new constraints on theoretical models of dark matter and dark energy, prompting researchers to refine their understanding of these enigmatic phenomena. In the realm of theoretical physics, the discovery of early massive galaxies has sparked renewed interest in alternative cosmological models. Some theorists propose modifications to the standard cosmological framework, such as the introduction of additional dimensions or modifications to the laws of gravity, to account for the observed anomalies. These speculative ideas challenge physicists to explore new avenues of research and develop novel theoretical frameworks that can accommodate both established observations and emerging data. The JWST's discoveries also have practical implications for future space exploration and the development of advanced astronomical instruments. By pushing the boundaries of observational capabilities, the telescope provides valuable insights into the technological challenges of studying distant galaxies and cosmic phenomena. It serves as a testament to human ingenuity and the collaborative efforts of scientists, engineers, and technicians who design, build, and operate cutting-edge space observatories. Looking ahead, astronomers anticipate further discoveries from the JWST that will continue to reshape our understanding of the universe. Future observations may reveal additional early massive galaxies, shedding light on the diversity of galactic structures and the processes that govern their formation. These findings will inform ongoing efforts to unravel the mysteries of cosmic evolution and deepen our appreciation for the intricate interplay of physical forces that shape the cosmos. In conclusion, the discovery of early massive galaxies by the James Webb Space Telescope represents a milestone in our exploration of the universe's origins and evolution. It challenges existing theories, inspires new questions, and underscores the dynamic nature of scientific discovery. Michio Kaku's perspective on these developments highlights the importance of embracing uncertainty and remaining open to unexpected findings in pursuit of deeper insights into the cosmos. As humanity continues to probe the mysteries of the universe, each new discovery brings us closer to unraveling the cosmic tapestry that surrounds us.